What is the formula for scan time?
How do we compute scan time?
Like the different factors that are involved?
How do we figure out what our scan time is? Go ahead, Ben.
TR times phase matrix times nex.
Very good. You don't want a candy cane? Times your phase matrix, times your NSA or NEX.
Define T2 image contrast, T2 decay, and how it is controlled.
All right, Mike.
All right, so in T2, fluid is bright and is dark. It is controlled by TE, and along with TE, enhances it. And it is accomplished once 63% of the churn first frame has been secured.
Very good. And what else? What is it called? What else is the name?
Spin.
Spin.
Discuss rectangular field of view. For rectangular field of view, there's like a rectangle. One side's longer, one's shorter. Depends on the body part you're doing. So like for, I guess, abdomen would have a rectangular field of view as opposed to a brain, maybe square or something.
You're close.
Either the frequency encoding is longer than the phase.
You're getting there. A square field of view means what? It's equal on all four sides, correct? So when we talk rectangular field of view, we're shrinking the image in what direction? Santa?
The frequency.
The phase. Okay, so if you think about it as we don't need to see all of this, right? What is our phase direction and frequency direction?
Frequency, the horizontal.
Frequency is what? We're not talking,
It's
we're
a
not
long-
talking K-space, we're talking looking at the image.
Interior.
Head to toe. The longest.
Which is our phase direction and which is our frequency direction?
The longest one.
Horizontal.
Frequency direction is the long axis of the image, okay? So this would be, right, anterior, posterior, superior, inferior. The long axis of the image is what? S to I. So that would be our frequency direction. The shorter anatomy is the phase. Whenever we do a rectangular field of view, the field of view always shrinks in the phase direction. So you always have to be very careful that you have your frequency direction and your phase direction selected so that if you do rectangular field of view, it will shrink in the A to P direction. You don't want to have these swapped, because if this was our phase direction, it would shrink in that direction and we would cut off anatomy. Okay? So your frequency direction is typically the long axis of the image. Your phase direction is the short axis of the image. So when we use rectangular field of view, which means it's uneven, Okay, so let's say that's a 26 field of view. It would be 26 by 26, but if we use rectangular, the shorter direction would be like 18 by 24. Does that make sense? Because it's going to shrink in the face direction.
Wait, so the short is always the frequency?
Phase.
No, the frequency direction is the long axis of the image. The phase is the short. Whenever you choose rectangular field of view, it's going to shrink in the phase direction, the short axis of the image. You ready? Who's next?
What makes an element MR accurate? An odd number quotient?
An odd mass number.
An odd mass number.
So in order for an element to be MR active, it must possess an odd mass number.
The T1 and T2 of water are
Did I not put times on it? Did I not write times? I meant to say the T1 and T2 times of water are,
one. That's a longer or shorter than actual number.
no, just the T1 and T2 times of water are long.
What the precessional frequency of hydrogen at 1.5 Tesla? I will usually calculate it. 4257 times 1.5. 63 something, right?
Thank you.
Okay.
Define gradient echo and how it is applied. Advantages and disadvantages. Gradient echo uses gradients.
To do what? So we've already gone over spin echo. Spin echo requires a 90-degree RF excitation pulse to flip the spins to the transverse plane, followed by a 180 rephasing pulse to rephase the spins. So how do we achieve a gradient echo? It uses a gradient to flip the spins, right?
With an opposite polarity.
Hang on, we're still flipping.
Flip angle other than 90.
Correct, with a variable flip angle, right? Typically less than 90. So if it's less than 90, what happens, Shirley? Not all the spins will reach the transverse plane. So give me an advantage of gradient echo.
Well, it's susceptible to metal, so you can see,
That's an advantage?
that might be a deal,
It's fast.
Gotta have the eye on the big prize. So a disadvantage or an advantage of gradient echo is what?
Faster, shorter TR.
Shorter TR, shorter TE, shorter scan times. Disadvantage of gradient echo.
Doesn't clean up the inhomogeneity.
The gradient of opposite polarity cannot clean up those inhomogeneities. It does not push past the transverse plane.
Opposite polarity one?
In order to rephase the spins, another gradient is used of opposite polarity. Meaning, if this is the fast end and this is the slow end, when the gradient comes down to rephase, the fast end will be applied to the slow side, right, to slow down the fast spins and to speed up the slow spins. So a disadvantage is it cannot clean up the magnetic susceptibility and homogeneity of the T2 star. When is it advantageous to not clean up those stragglers, the magnetic susceptibilities?
Strokes, bleeds.
More bleeds, right. Because the iron in the blood, we want to see that. If we use a 180 rephasing pulse, it's going to push past the transverse plane and it won't contribute to the image and we won't see it. She's like, bring it. I'm ready.
I'm never ready, but that's,
You'll be diabetic, but you'll be
yeah.
ready.
Hey, well, this one, here we go. All right, maybe I'll take this back. Describe the two bandwidths and what controls each one. Also define the bandwidth.
There's two types of bandwidths, name them.
Transmit and receive.
You have the transmit and receive bandwidths.
Okay, tell me about the transmit bandwidth.
The transmit is in like an intrinsic factor. That's something we can't control or change.
Okay, how is it controlled?
Automatically by the computer.
Slice
Slice
thickness.
thickness, yes. Slice thickness, change effects of
And the
frequency.
slice thickness
Yeah.
controls
The slope,
the steepness of the slope, very good. So if I want a thick slice,
you're gonna use, it'll be a shallow slope.
a shallow slope, if I want a thinner slice,
It'll become more of a steep slope.
very good, that was easy. Now tell us about receive bandwidth.
That one we can control.
What is the receive bandwidth?
It helps determine our sampling rate.
Give me that candy back.
It helps to
The
determine
range
the
of
sampling
frequency.
It's, the receive bandwidth definition, you can say, is the range of frequencies that we are sampling.
Okay.
And how does that affect our image? So if we're talking about the range of frequencies, the example I always use is the window. You have construction outside, jackhammers going, the window's closed, we don't hear it that much, right?
Right.
We open it a little bit, we get a little bit of that noise. The
Okay.
more you open it, the higher range of frequencies that you will sample, but it also invites in more noise. So you have to be really careful with receive bandwidth. Was that him? Oh, nope. I'm volunteering, you guys know.
Describe the different types of magnets. Well, let's see, what are the different types? There's the permanent magnet. There's the superconductor.
Conductive? Mhm.
And the other one is no.
Anybody? Resistance. So tell me about the permanent magnet. What kind of a field, magnetic field does it have?
Vertical.
A vertical. Permanent magnet, what kind of field? Vertical. And the superconductive, horizontal. Okay. Why is that important? The direction of the magnetic field. What does that affect?
The French field?
Very good. What is the fringe field?
The area around the magnet?
Around the ball.
And why is that important?
It's always there.
Because if they haven't implanted a medical device, it's only been tested for the longitudinal, the way that it.
Yeah, you're diving into it, a different thing, but you're right. The fringe field is the field, the magnetic field right outside the magnet. Remember, as soon as that door opens, the door to the magnet room, boom, you're in the magnetic field. Anything that's inside the room but outside of the bore is the fringe field. So if it's a horizontal field, it's running this way, correct? So a fringe field on a horizontal magnet is stronger or weaker than a vertical?
Stronger.
Why?
Yeah.
It's cylindrical like this. On a vertical,
It's up and
the fringe field is much tighter because the fringe field is much smaller and it's vertical. Okay, so the chances of you walking in there with a metal object in your hand to a superconductive or a horizontal magnet, it'll get picked up a lot quicker than if you go in to a room that has a vertical field with a metallic item in your hand. Okay, what is a factor that controls how fast or how quick an object gets picked up and taken into the
it's size.
It's mass
Proximity.
and proximity to the magnet. So the closer you get, the higher velocity and the quicker it will go in, okay? A lot left in here, guys. Oh, your candy cane.
Name and explain the physical gradients in MRI.
What are the physical gradients?
Physical. Oh, is that active and, no, that's shielding.
Physical gradients. Ben, is that a hand up? Go ahead.
Is that X, Y, and Z?
X, Y, and Z. X is
Is that
Y,
Vertical.
sac. Or ska, I'm sorry, ska. Sorry, Jen. Sagittal, coronal, axial. I'm a little dyslexic tonight. So why are they important? Why are the physical gradients important?
Because that's how you find the patient and the,
Depending on what plane that you are scanning in, you have to turn on that particular gradient, whether it be X for sagittal, Y for coronal, Z for axial. Okay? Just picking one.
Define K-space, how it's filled, when it's filled, etc.
What is K-space?
K-space is what holds the image in the computer.
It's a temporary storage for the data that's picked up by
By the coil.
the receiver coil. Very good.
So it's more concentrated in the center.
What do you mean by concentrated?
It's stronger in the center.
What kind of data fills the center of K-space?
Contrast.
Contrast. What kind of data fills the outer lines of K-space? Spatial resolution. How is K-space filled? It can be left to right, right to left, center to out, out to center, but how is it filled? One line at a time. Every time a TR is run, a line, right? Is this coming back to you guys now? Every time a line, or a TR is run, a line of K-space gets filled, okay? When is K-space considered complete?
When all lines are filled?
When all of the lines are filled. What is very important about the steepness of the slope of the phase encoding gradient? The slope of the phase encoding gradient changes. If it stayed the same line of K-space would get filled each time. Okay? The steepness or the slope of the frequency encoding gradient remains unchanged, remains the same the whole time. Okay?
To achieve high SNR, use a course, or is it use a blank
Right. For high signal to noise,
high signal
use a
course?
Y.
Bigger pixels, smaller matrix,
Give me a number. What do you?
128, 128.
128 by 128. Okay, so remember, the lower matrices will give higher signal because the pixels are, there's less pixels and they're bigger. Okay? I'm not stopping till I'm out of candy canes, so.
What is field of view? How does it affect SNR? Field of view is the anatomy that you're covering, and the bigger the field of view, the less signal, or more signal.
More signal. As you increase field of view, your signal increases, but
Your resolution
your
goes
spatial
down.
resolution will
Decrease.
decrease. These brave souls back there.
Describe all of the components of the matrix. The voxels. What do you mean by matrix? The
What is the matrix?
matrix is the
Pixels.
sum of voxels.
Pixels inside.
Pixels are
Pixels.
2D, right?
And
Voxels are 3D.
Okay.
The matrix is composed of
2D and 3D.
two
2D.
elements.
2 elements. Right.
Coarse and,
You have a phase encoding,
oh yeah, and
Right?
frequency.
and the matrix, you have a phase matrix and you have a frequency matrix. Which number is the first number if I rattled off 256 by 190?
Frequency.
Is the first one. Frequency.
Frequency is always the first number.
And phase is the second one.
Correct. And what was the rest of that question?
That's it. Describe all of the component of the matrix.
Okay, let's take it a little bit further though. So if I want to increase signal, I already know that I will use what kind of matrix then? a coarse matrix, right? So typically, this is going a little bit off. Let's say I'm running a sequence and it's 256 by 256, but I want to gain a little bit of signal. So I will decrease or drop down my phase matrix. By doing that, I will increase signal, but I will also do what? Decrease
Resolution.
Spatial contrast.
time. Okay? You think to yourself, well, I'm decreasing this, I'm increasing signal, how am I decreasing time? It decreases time. So if you're ever looking for like something quick and not too subtle, or I should say more subtle, you can drop down your phase encoding, your phase matrix, just one step, and it will decrease your time and it will give you a little bit more signal. Okay? That's kind of a sidebar thing, but.
Discuss NSA for next. So, design precision.
Okay. What does that mean? What is NSA or NEX?
The number of filling the line of K-space.
Is it the number of times when you have to
Number of
go around and take the
Sampling?
same image as sample?
Correct. Okay, so it's the number of excitations or the number of signals average. So as you increase your NSA or your NEX, you're actually filling that line of K-space again and again and again, and it gives you more signal. Now, what's a disadvantage of raising or increasing our NSA or our NEX?
The
Time. It's going to increase our time. Okay?
So when you cut it back, what's the disadvantage? I guess what's the disadvantage?
Of decreasing your NEX, you're losing signal.
So the picture comes out a little.
It'll be grainy, it won't be as sharp, it won't be as, you won't have as much signal. So let's say you're running at 2 NEX and you cut it down to 1. You're gonna get half the signal. Okay, you're gonna cut it by half. Like when you're running 4 NEX and you cut down to 3 NEX, you only lose about 20%, maybe even a little less than that. Okay, but you have to be careful, especially when you're halving it. Because when you half it, you're halving your signal.
Okay. What are the parameters for a T1 gradient echo and Kurzweil echo?
Parameters for a T1 weighted gradient echo include flip angle.
Include what?
Flip angle. Remember your TR and your TEs.
I'm thinking short.
Yes, yes. Your TRs and your TEs, when you go to gradient echoes, for T1, whether it's T1, T2, proton density, it's going to stay the same. So T1 is always going to be short TR, short TE. A T2 is always going to be a long TR and a long TE. When you get into gradient echo, it's the size of the flip angle that makes the most difference. Okay, so if you want a T1 weighted gradient echo, you're going to use a larger flip angle. Okay, if you want a T2 weighted, a shorter. Now remember, your TRs and your TEs are shorter anyway going to a gradient echo. So it's not going to be like a spin echo where for a T1, let's say you have a 500 TR and a 25 TE. When you go down to a gradient echo, and a 90-degree flip angle, when you go down to a gradient echo, let's say it might be 100 for your TR and 5 for your TE. Okay? just remember that the TRs and TEs, still gonna be short, short, long, long, whether you're spin echo or gradient echo, but they're much shorter in your gradient echo. The big component of that is your flip angle. Okay, make sense? We're getting down to the last couple, guys.
What is TE? Echo time? That's when the signal is induced in the coil. It controls T2.
Yes.
They acquire the signal at the peak of the echo. It's when you acquire the signal at the peak of the echo.
Louder, so big.
When you acquire the signal at the peak of the echo.
Okay? I'm dying. Hasn't done well.
Let me see.
You haven't done it.
Oh, my died.
I'll give it to Brittany.
To achieve high spatial resolution, use a fireworks.
Give me a number.
1024 times
That's a pretty good size one. Okay, I'll buy it. You look hungry.
What is TR?
What is TR?
The time of repetition or repetition time. The time between frequency?
The time of each
Excitation.
One excitation pulse to the next. That wasn't so bad, was it?
The good part is if you don't know it, someone else will.
Oh, but you have to participate.
Tell me you didn't have to do
I changed my mind.
I think you might mess it up.
I don't know the answer. Discuss phase and frequency as it pertains to image direction.
We did that.
I don't know, you said something about the rectangle or the square shape of it. Sorry.
This is an easy one. We already went over it.
Well, you said the frequency was the long axis.
Correct.
The rectangular and.
Hang on a second. The frequency direction is, whether it's rectangular or square, is going to be the long axis of the. When